Thank you.
Okay, then the last speaker of the day is going to be Luca Spada, and the title of the talk is To Veil to Rigs. And Luca, take the stage.
Okay, thank you very much. I hope you can hear me well. Well, first of all, thanks for the opportunity to speak here. I only recently learned about this Ithaca community, and I think it's a very nice ideas. And also, thanks for accommodating the schedule of the workshop to my location in time and space. This is still morning for me. So what I want to mention at the beginning to start with is that this is not really a talk about category theory. It's more a talk that tries to check some idea in category theory in real life. After all, science is made also of experiments. I'm sorry, I still hear my echo. Maybe
I do not hear it.
Okay, so
we can't hear you here. Sorry, you hear it, but
let me try to check this.
Pepe, we didn't understand what you said, whatever you said.
I'll just say that we don't hear any echo, so I'm sorry. Luca is
Actually, I do hear it, but it's not that loud. But there is one, yes.
that's because I'm a little bit.
What about what about now? No, I still hear it. It's strange. Let me check. So this is okay. Maybe no. It's this. What about now? No, yet. I still well. I can survive with the echo. What about you? It's
Personally,
like...
personally, I do not hear it. So for me, there is no problem.
Yeah, it's really okay. It's very low. Thank you.
Okay. Okay. So I was saying this is going to be rather an experiment. What I want to do is to test an idea that was born in category theory in real life. The idea that I want to test is this idea of extensivity. A category is called extensive when the canonical functor from C over X times C over Y into C over the coproduct of X and Y is actually an equivalence. Now, this is a very basic property that is shared by many categories of spaces. For instance, any topos is extensive, on sets is extensive, topological spaces are extensive. And it's also a very basic one. In a sense, it's saying that that the object of this category can be put together without adding too much information. Now, I'm not an expert of the theory of extensive categories, so I refer you, and I use also this opportunity to make some advertisement to the Tackle conference that will take place at the beginning of July. There, Matthias Menni will give an invited talk, and I'm quite sure he will speak extensively about extensivity. So what I will do is to consider a particular case of an extensive category and see whether this property of extensivity actually gives some geometrical flavor to the category. Of course, I want to do it algebraically, so I will actually consider a category that is coextensive, that is dual to an extensive category. Now, the category I want to consider, you cannot see this, right? The category I want to consider is the category of rigs. Rigs, it's a name that is like a sort of PAM because it stands for rigs without negatives. So that's why there is an N missing. They are actually unital commutative semiring. Now, the semiring theory is very vast, and semirings have been studied from many, many different perspectives, computer science, linguistics, and I guess many more. So not even the naming conventions are well established. So let me use this slide to explain what I mean by a ring. For me, a rig is a unital commutative semiring, which means that we have two operations that are conventionally written as times and dot and plus. They are both associative and commutative, and there are two neutral elements, one for the plus and one for the times. And of course, as you expect, there is a distributivity law that holds both in the finite case and in nullary case. So we have that the times distribute over plus, and multiplying by 0 annihilates. Okay. Examples of rigs abound. This is why it's an interesting class of algebras, because, for instance, any bounded distributive lattice is a rig. Also, any commutative unital ring is a rig. So it's a class of algebras that contains really a lot of algebraic structures of interest. Also, the Boolean algebra 2, seen as a distributive lattice, is of course a rig. And also the structures that are typically considered in tropical geometry, like are with the plus infinity, the minus and the plus, is a rig. Also is a dual version with max. The natural number with plus and times are also a rig, or the positive reals are also rigs. And as I was saying, the category is coextensive. So it's dual to a category, it is extensive. Now, what is the idea that was proposed by Matthias Menning? Well, actually, was proposed by Bill Levere and then pursued by Matthias Menning. He's the guy that convinced me to study this thing. So he's responsible for this talk in a sense. If extensivity, it's really an axiom that it's really a property that tells that the category is a category of space, then if one tries to study rigs, there could be a geometric intuition guiding the study. And actually, this is quite surprising, because the structures are quite general. So in principle, you cannot expect that many results of classical algebraic geometry, which relate to commutative unital ring, immediately generalize to all rigs. We will see that a couple of geometrical ideas actually work out. Now, before giving you the definition of veil rigs, let me mention another couple of categories that I will consider. The first one is the category of applies category of two rigs. So if you consider a morphism from 2 into any rig R, this must satisfy this series of equality. That is, one must be the 1 in 2 must be sent into 1 in R, but the 1 in 2 is idempotent, because 2 is not to be confused with Z2. It's the distributive lattice 2. So 1 plus 1 is 1. Then you use that as a homomorphism, and you get that also the 1 in R must be idempotent. Also, the vice versa holds, in the sense that if 1 is idempotent, then 0, 1, then if 1 in R is idempotent, then this rig contains a copy of the distributive lattice. Thus, we have that a morphism F from 2 to R exists if and only if the 1 in R is idempotent. But this means, by applying distributivity, that any element is idempotent, because I can always write x plus x, like x times 1 plus 1, and get that is equal to x. So actually, the category of two rigs is equivalent to the category of idempotent rigs, or at least additively idempotent rigs. So I will call a two rig an idempotent rig. In any rig, actually in any monoid, one can use the monoidal operation to define a preorder. And this is called the natural order, because it's it's a natural way of defining it. So one says that x is less or equal than y if there exists an x such that x times z is equal to y. Now, a few observations. First of all, in a rig, there are two such orders because we have two such monoidal operations. And I will use mainly the additive order. So I will write less or equal for the additive one. The second simple observation is that rig homomorphism must preserve this order. Another interesting one is that if you consider a two rig, so an idempotent rig, then the less or equal becomes a partial order. A further remark is that this order in rings is not really useful because it's always the indiscrete order, because of course if you have a negative number, then this can be easily satisfied. A final thing that will be useful later is that a rig in which one is the top element is called an integral rig. Why am I saying this now? Because the fact that one is a top element can be written like this. Any element must be below one, so it means that x plus 1 is equal to 1. And in particular, this must hold also for 1. So we have that 1 plus 1 is equal to 1. As we have seen previously, 1 plus 1 equal to 1 implies that the rig is idempotent. So these integral rigs are always idempotent. So basically, there are three categories that will be of interest in this talk. They are the category of all rigs, then the subcategory of two rigs, and then the subcategory of two rigs, which is given by the integral rigs, in which one is the top element. Okay, these rigs are at least intuitively similar to rings, so one can try to generalize some main ideas in commutative algebra. For instance, the notion of an ideal makes sense, make perfectly sense also in rings. So I will call an ideal just what is called ideal in the case of rings. It contains 0, it is closed under external multiplication, and is closed under sum. Also, the definition of a prime ideal makes sense because we can say that I is prime if every time it contains a product, it must contain at least one of the two factors. What is a new thing because of this order that appears in rigs is the idea of a saturated rig. A saturated rig, it's a dual, in a sense, a dual notion to, a saturated ideal is a dual notion to a prime ideal because it states the same condition using plus rather than times. Of course, this notion doesn't have much sense in rigs because, again, 0 belongs to any ideal, and any element together with its negative gives 0. Of course, you can have a correspondent notion of, and this is again obtained by switching the times and the plus. So 1 is always in the filter. The filter is closed under external sum, and the filter is closed under product. And then again, you have two similar notions of primeness and saturation, which are again obtained dually by switching plus with times. What makes the study of rigs a little bit harder than the study of rings is that there is not such a nice correspondence between ideas and congruences. So in a sense, I guess it could be said that the category is not protomodular. Still, any ideal induces a congruence by using this definition, but not all congruences are induced by ideals. And not even filters are of any help, because the idea is that filters are the preimages of 1, ideals are the preimages of 0, but there are quotient of rigs that only collapse elements in the rig which are neither 0 or 1. Hence, this cannot be captured by ideals or filters. Still, there is a nice Galois connection between, an adjunction between ideal and congruences. And the saturated ideals are the ones that are fixed by the adjunction. And using the order that we saw before, they can also be characterized as the downward clause in the order. One, let's say, fundamental result in commutative algebra is the existence of enough prime ideals. And this is already quite surprising that such result also holds for rigs. The problem is to find the right way of stating it. So the prime ideal theorem in rigs says that if you take any two subsets of a rig R, and they are such that the ideal generated by S, so the smallest ideal contains S, does not intersect T, and T is closed under multiplication, then there exists a prime ideal P, which extends S and still does not intersect T. Now, the stronger version of this prime ideal theorem, the one which is needed in this talk, is that if in addition I assume T to be a filter, then I can say that there exists a saturated prime ideal P and a saturated prime filter F, such that P extends S, F extends T, and they still do not intersect. So what I'm saying is that if I take an ideal and a filter which don't intersect, they can be both extended to a saturated prime ideal and a saturated prime filters, which again don't intersect. Okay, once you have this theorem, you can prove something interesting, because one can obtain a sort of Null-Stellensatz result. Before doing that, I need to introduce a little bit of notation. So, as usual, those are all quite classical notation in commutative algebra, apart from the ordered version that are this drad and codrad. The first one is the square root of S, which is the set of elements X in R, such that sum of their power goes into S. The other one is, again, not very standard, is it's sort of, again, dual of the former notion with the times instead. I'm sorry, is a dual version that corresponds to filters rather than ideal. So the set of, we can call divisor of S are the X in R, for which there exists a Y, such that X times Y lives in S. And then the other notion are all quite common. So the radical of S is the intersection of all prime ideals that contains S. The co-radical of S is the intersection of all prime filters that contain S. And then you have the version that take into account the order, which are the drad, that is the intersection of all prime saturated ideals that contain S, and the codrad, which is the intersection of all saturated prime ideals that contain S. Now, the Null-Stellensatz I was mentioning, it's this. It says that if you take any ideal I, then the square root of I coincides with the radical of I. In addition, again, a stronger version which takes into account the order says that if I is also saturated, then the square root of I also coincides with the d radical of I. For any filter, we have that the set of divisor of the filter is equal to the co-radical of F. Okay, let me get finally to the notion of Weil rigs. What I mean by that, again, if we have to use this, if we want to be guided by the idea that the dual category to rigs, it's a sort of geometric category, then points should occupy an important part. So in a category of spaces, points with a objects with a single point are the basic bricks. What is a point in a category with a terminal object 1? Well, this is quite common. It's just an arrow from the terminal object 1 into X. Notice that in many category of spaces, there may be several non-isomorphic objects with just one single point. So I will call dually a rig Weil if it has a unique map into the initial object. Okay, I hope it makes sense as a definition. Since we want to look at basic object in the extensive category, we look at their dual object in the coextensive category. So I will try to investigate these Weil rigs. Now, notice that the notion of so being Weil, it's something that is connected to the category in which you are considering this property, because it's related to initial objects. In particular, in rigs and in the category I illustrated before, there are different initial algebras, because in the category of rigs, n, the natural number, gives the initial algebra, while in the category of two rigs is 2, the distributive lattice 2 is the initial algebra. So we need to have a more precise notation that is I will call 2 Weil a rig which has a unique morphism into 2. So of course, it makes sense to consider 2 rigs which are Weil, but it also makes sense to consider rigs in general that are Weil in the category of 2 rigs. And why does it make sense? I think one motivation is the remark that follows. A rig has a morphism into 2. If and only if it is not a reduct of a ring. So I'll call those rigs proper. So the fact that a rig has a morphism into 2 witness the fact that for some elements there are no opposites. That's why it makes sense to study in general rigs that have a unique map into 2. Apart from the idea that I explained before, that Weil object corresponds to the basic algebras in some sense to the basic algebra in this category. Okay, I hope what I'm explain makes sense. You feel free to interrupt me at any time if if you have questions. Okay, so what is the connection between 2 Weil rigs and prime ideal? Well, it's a quite simple one. The observation is that if P is a prime saturated ideal, then its complement is a saturated prime filter. And if you define a morphism in this way by sending the prime ideal into 0 and the complement into 1, you actually obtain a rig morphism. What it should be noted is that this is not in general the quotient of R over P. So in general, this is different from 2. But in a sense, a saturated prime ideal makes a bipartition of the rig, which allows to define a morphism into 2. And once you have made this observation, it's also clear that if you have a morphism from R into 2, then the inverse image of 0, it's again a saturated prime ideal. So it is clear that 2 assignments are 1 the inverse of each other. So basically we have a bijection between saturated prime ideals and morphism into 2. This observation allows to prove the following characterization. For any rig R, we have 4 equivalent conditions for being 2 Weil. One is that the definition, there is a unique morphism into 2. The other one is the one that we just observed. There is a unique saturated prime ideal. The third one says that R is veiled if and only if it is the disjoint union of its d radical and co-d radical. So they have intersection empty set, and together they give the full R. And the fourth one is a sort of axiomatization in geometric logic, because it says that a proper rig, so a rig that at least has one morphism into 2, is a two-veil rig if there exists an n, if for any x, either there exists an n such that x to the n goes below 0, or there exists an r such that x times r goes above 1. Now, since two rigs are always proper rigs, a two rig is veiled if and only if satisfies this condition. Notice also that being a proper rig, it's also it can also be written in first order, and actually the proper rigs form an algebraic category, which is something of interest in itself. Okay. Once we have this characterization, we can, which is in a sense unexpected, because again, one should not expect that all techniques of commutative algebra should generalize this to this theory. Once we have this characterization, we can consider the inclusion of veil rigs into the category of rigs. And it turns out that this inclusion has a right adjoint, because if we consider any proper rig, then we can define WR as the union of the d radical and the co-radical or co-d radical of R. And we obtain that this is actually a subalgebra of R, and is the largest two-veil rig contained in R. Together with the fact that whenever you have a rig homomorphism from V into R, this factors through this biggest two-veil subrig, it gives that the inclusion factor as a right adjoint. A nice application, which again uses this geometrical intuition of this result, is about pseudo-constant maps. Define a pseudo-constant map as a map that co-equalizes all the points of x. So it's a map f from x into y, such that for any pair of points of x, f of the first point is equal to the f of the second point. Now, this, if the idea of a pseudo-constant map makes sense in a category of space, you would expect that such a map would factor through a one-point object in the category of spaces. This dually corresponds to the fact that rig morphism F, which is dual to a pseudo-constant morphism, factors through the veil rigs WS. Okay. Something about subdirectly reducible, because in the category of spaces, points are the building blocks, but in a category of algebras, usually are subdirectly reducible algebras, the ones that are considered the basic blocks. So that one would expect some relation between subdirectly reducible rigs and veil rig. Unfortunately, the two classes are not comparable, because we have found two simple veil rigs, two simple rigs. One is the one on the left, in which all products goes to 0, which is clearly veiled, because the only way of sending into 2 is by taking these three elements and sending them to 2 and sending only one into 1. But unfortunately is not subdirectly reducible. So it says that sorry, it's the other one that is subdirectly reducible but not veiled. So it says that not all algebras are subdirect product of veil algebras. For the other example, consider the same rig with 4 elements, but let's just make B an idempotent element. Then it is not veiled because we can decide whether to send B into 0 or 1. So we have at least 2 morphisms into 0, 0, 1, but it is subdirectly reducible. So it seemed that in this case, the geometric intuition did not guide us well, but actually it did, because although the 2 classes of algebras are incomparable, so although Weil rigs and subdirectly irreducible rigs are different classes, 2 Weil rigs still are basic blocks in the category rig because they generate the variety. To see that 2 Weil rigs generate the variety of rigs is very easy. It is enough to notice that the natural number generate the variety, because the natural numbers are a 2 Weil rig, because a rig homomorphism must preserve 0 and 1, and n is generated by 1. So once you have decided where to send 1, all the rest is determined. But what can be said in addition is that the finite 2 Weil rigs generate the variety of rigs. So how did we prove this result? We actually show that n is the subdirect product of a family of quotients given by this, in which I'm taking the quotient of the natural number by the congruence that is generated by the pair k plus 1. So they are the k-potent quotients of n. It's not hard, using the characterization above, it's not hard to prove that these rigs are all Weil rigs, and they are, of course, all finite. Similar thing happens in the category of 2 rigs and integral rigs, but for different reasons. In this case, the finitely generated free objects in the category 2 rig and I rigs are subdirect products of finite Weil rigs. As a consequence, we obtain that the varieties of 2 rig and integral rigs are generated again by their finite Weil rigs. So it seems that the geometric intuition that guided this research, it's valid. There is some geometry going on, and this finite Weil rigs seems to have to play an important role. And it would be nice to explore more the geometry of these algebras by really investigating curves and manifolds defined over at least 2 rigs or even more general rigs. But for the moment, this is everything I have to say. So thank you for your patience.
Thank you very much, Luca, for this very nice talk. And we move to the question time, so people can unmute themselves and ask questions. So while people think, I actually would have really too many questions for this talk, so maybe we'll start just with one. Do you have a reference for the first statement that you made concerning the fact that the co-slice category is equivalent to the 2 rigs are idempotent rigs? Do you have a reference for that?
Aren't you happy with the explanation I gave?
Yes.
Because I think that it's written in many places, but the proof probably is not written anywhere.
I'm very happy with your proof. It's just maybe I want to cite it somewhere, and it would be
I think it's just a simple observation. It's not really written anywhere, but it was observed in several places. I think that Matthias Manni already did it in a paper with José Castiglioni, I guess. I can give you a reference to that, but yeah, it's just an observation. Probably you won't find the proof, the explanation in the paper.
And then I have another question. So did you consider like the notion of a spectrum of a...
There is, Matthias writes that Bill certainly mentions that in core varieties in ring geometry.
Thank you.
Thanks, Matthias. I didn't know you were there.
If you want, Matthias, you can also unmute yourself and speak.
Thank you. I took note of it. And then I have another question. Did you consider the notion of spectrum of a rig and like going in that direction of enhancing your Nullstellensatz?
Of course, it makes a lot of sense to consider the spectrum. It depends what you mean by that, because in a sense, the fact that we are considering the opposite category of rigs as a category of spaces has already the idea of using a spectrum functor from rigs into spaces. If you mean rather to characterize topologically the spectrum of a rig, then I don't know whether this is going to be easy. So what do you mean by have you considered the spectrum? Because that can be a functor or a topological space.
I meant topological space.
Okay. No, well, I don't think it's going to be easy. It's really an interesting question, but yeah, I'm afraid it's not going to be very easy. Oh, yeah, I don't know. You know that the characterization of the spectrum of commutative unital rings required a complicated construction due to Oxter. I know a little bit that construction, and I don't see how to generalize to rigs. But yeah, would be definitely an interesting finding.
Okay. Thank you. I will open the mic to other people, but I would have other questions. So if someone has questions, please chime in.
Ciao, Luca.
Ciao, Matthias.
You mentioned did I understand correctly that proper rigs form an algebraic category?
Yes, I think we discussed that when you were in Salerno.
I don't remember.
Because it's the category of rigs that have a morphism into two.
True.
And this should give that it is automatically an algebraic category.
Okay.
No, I could be wrong. I remember that we were discussing this a few months ago.
I need to think more. Sorry,
Okay.
it was a distraction. Thanks.
No, I should also I should also think of it, but we can discuss it again offline.
I think your argument is approved, to be honest.
Already?
Because they are the algebras for a very simple monad, which will preserve the correct equalizers that you need to preserve in order to have the monadicity. I think it's true.
Yeah, I mentioned it only in passing, but maybe I should have checked it more carefully. But I remember that we discussed this when Matthias was visiting me in Salerno. But yeah, thanks for the remark.
But can the things that you presented today, is there a preprint online already about this?
No, there is not a preprint, but I have a draft. I can send it to you. Oh well, we have a paper that we submitted, so I can send you the preprint if you want.
I would be very happy to see it, but don't feel like if you want, I can wait. But I would be very happy to see it. Yes.
No, I have to ask to my co-author, which I forgot to mention at the beginning. I think this is joint work with Gavins and John. So I have to ask him, but I think he will be fine with that.
And then I have a final comment to the community of category theorists. The word to rig has already a meaning. and it is a bit confusing.
What is the meaning?
It's like it's more the categorification of the notion of a rig.
It's a category with two
I see.
operations. Well, there are at least two different notions of Turing, I think. Fosco was expert about it.
So in this sense, I'm not trying to say that like the community has the right notion. I don't claim that. It's just that it
Yeah, I
does
see.
it does generate quite some. I thought your talk was going to be about something very different, to be honest.
I see. Well, again, Lovier calls them rigs, Matthias calls them rigs. There is a lot of different naming convention in the community of semigroup,
Rigs is okay.
semirings.
Luca, rigs is okay. Is
It's two rigs. Okay,
two
I see.
rigs is a problem. Rigs is
Okay,
fine.
probably then I should put a slash after the
Mm.
two rather than an hyphen.
If you put a slash, then it's clearly a comma. Or you put a comma, old-fashioned style. A slash is fine, or arrow downward.
But Luca, this is just being like I understand. Like this is not an interesting comment. It's just it can.
No, it is interesting. We switched to the notation to rigs again, suggested by Matthias, because integral rigs also begin with I. So I rigs, we reserve the name for integral rigs, which are also of interest. I was happy with rigs, but now that you are telling me that there is a clash of notation, I will think of something else. Probably a slash should be fine.
So a K algebra is very classical algebra. So, and there's no way to solve that really.
Yes.
So, sorry, since I'm going to meet you next week, I don't know if I should take time, but if no one else has a question,
I'm free.
If your two rig is finitely presentable, is the largest base of algebra also finitely presentable?
Yeah, it's an interesting question, and the problem, as we mentioned several times, is that we don't know many nice property of finitely presented object in this category. So it's not easy to use your hypothesis of finitely presentation of the initial rig. So I don't know. I cannot give you an answer now. I can think of it. It's an interesting question, but I don't know how to use easily the fact that the rig is finitely generated, finitely generated or finitely presented.
Yeah, I don't think it's easy. You're right. Thanks.
Okay, I have to close the conversation. So we thank the speaker one more time. Thank you very much, Luca, for this interesting talk. And guys, we are done for today, but don't leave. Remember, we will have other instances of Ithaca Fest. And most importantly, there is the workshop happening in December. And the webpage is already online with information about it. So check out both the workshop and the next event of Ithaca Fest. We also thank all the speakers that have joined today. And yeah, now